I don't always talk to other people who are blue carbon scientists, and I write papers, and I don't always know if people read them or they get out there. So hearing people being excited about my work is really energizing, and I'm going to bring this energy to the presentation. And we're going to get real excited about some national scale stuff, and we're going to get excited about some maps. You ready? Yeah. Okay. I just want to take a second to acknowledge the funding sources that have sponsored these projects that I'm going to be talking about. I'm really going to be talking about 3 projects overall. One of them, which just wrapped up this year, a NASA Blue Carbon Monitoring System project, an NSF Research Coordination Network, and a project that I've been doing with the US Geological Survey and the Nature Conservancy on taking some of these maps that we've generated at the national scale for those first 2 projects and downscaling them so that they're useful for state-level stakeholders. And of course, I'm supported by the Smithsonian, and I should acknowledge some co-authors on the unpublished aspects of this work. Okay, so today we've been focused a lot on kind of this scale of inquiry, people who are on the ground who have to make hard decisions on what to restore, when to restore, and how to do it. And a lot of your interpretation or your experience with kind of national scale stuff might be me calling you on the phone, bugging you, asking you, hey, can you like fill in a couple numbers in this spreadsheet so I can aggregate it and report it at this national level. But I really am a big believer that this type of scaling up of all the work that you do on the ground is bearing a lot of fruit, and that we're getting into the place where these 2 types of inquiry can start feeding back on each other. And you know, by all of you helping us with syntheses and us doing these national scale reporting, we can turn that around and start offering more decision support, more help with planning, and especially with restoration and these wetlands being such carbon bombs when they degrade, helping integrate more knowledge about the efficacy of restoration efforts. So this is kind of what I see where we're at now, and this is where I'm hoping that we can be in the next few years. So just an overview of my talk. I'm going to be giving a quick overview of the last few years of mapping in the blue carbon sphere at the national scale. I'm going to make a quick pitch on my project I'm currently managing, the Coastal Carbon Research Coordination Network. And then I'm going to talk about how we've taken some of those products and made them more relevant to state and local level managers who are interested in greenhouse gas reduction opportunities. So 2018 was really a banner year for blue carbon at the national scale. Ariana went over a lot of this, but we did have coastal wetlands included in the second State of the Carbon Cycle report for the first time. And that's not just the US, but also Canada and Mexico. And of course, the US National Greenhouse Gas Inventory, we were one of the first countries to include tidal wetlands in our reports to the International Panel on Climate Change. So this is a pretty educated audience, but just a quick review. This is the minimum biogeochemistry knowledge that you will need to understand the rest of my talk. So wetlands, they take in carbon, we know that, and they put out methane too, and this methane, the amount of it is really dependent on salinity, with saline wetlands putting out 0 to very little methane, and brackish to fresh wetlands putting out a pretty good, substantial amount of methane. So what kind of data goes into a national scale accounting? Well, we have to combine 2 very disparate data sets. We have to essentially multiply for all the different types of wetlands that we can map. We need to have emissions factors, which are big lit reviews, big spreadsheets, averages, which tell you things like how much methane do these saline and brackish wetlands put out, how much do fresh water, and then obviously like how much soil carbon burial is there. There's a lot more emissions factors that go into these, but these are kind of the big 3. These are the most impactful emissions factors that we found. And we have to combine that with activities data, which means the amount of a land cover type or a change type that will affect emissions or burials. So activities data, that's kind of a fancy way of saying maps. And in our accounting, we combined 3 different types of map layers. It was the Coastal Change Analysis Program, which is a 20-something class, thematic land cover map. This is all San Francisco Bay, which has 6 types of tidal wetlands in it, 2 types of salinity, 3 types of vegetation. They also put out change products every 5 years. Here you can see just change highlighted in red. In South San Francisco Bay, a lot of these are prograding wetlands, and some are wetlands that are switching between management classifications. Some of them are impounded wetlands that are becoming bare land or drained, and a lot of interesting salt pond things going on. And then we also created a map of the probability of an area falling below the highest spring tide lines, and this is kind of our map of including land cover types as within the coastal inventory or outside of it. So the NASA project that started this off was very focused on uncertainty, and I know people, like, well, when you're focusing so much on uncertainty, it just means you don't know what you're talking about. I think it's that quantifying uncertainty and propagating is a lot more constructive than that. And by propagating uncertainty, we found some really interesting things. First of all, we did find a net emission scenario at the whole of the U.S., and a lot of that's driven by big losses in the Louisiana Delta, and of course we included a lot of tidal freshwater wetlands, which put out a lot of methane in our accounting. But this scenario overall, the uncertainty varied by an order of magnitude. Where's that coming from? Ariana showed this earlier, but a lot of it comes from our data sets themselves that we use to construct these emissions factors, particularly methane, and a lot of the assumptions that we make about the power of methane, and what happens to soils when they are eroded. The maps are pretty good. Not too many complaints there. So the project that I manage now, the Coastal Carbon Research Coordination Network, is really carrying the torch of this NASA project forward. Our goal is to accelerate the pace of discovery in coastal carbon science by serving you with data, tools, and synthesis opportunities. One of the most visual and apparent ways that we've done this is we've taken a lot of the data that we aggregated for the US. We actually were really deliberate with how we organized and managed that data, how we made it public. And we've been helping other researchers make their data public and to aggregate it all into a common framework where everything's transparent, everything's traceable, and everything's citable. So if you submit data to our network, you're never going to get lost in the syntheses. You're always going to get credit for your hard work. And hopefully this can save a lot of other people time when they want to do their inventories. Right now, I think we have over 4,000 soil cores from all around the world. We have all continents, and we have the big 3 wetland types represented: seagrasses, marshes, and mangroves. We are also organizing topical working groups. Right now, our soils working group is winding down. Our big goal is to take this soils data that we've aggregated, to merge it with open source R-based models, and to come up with tools and metrics that are useful to stakeholders like you. And so my pivot back to kind of my mapping work is that we realize that it's not just easy as saying, hey, we made this thing, will you use it? That we need to be in meetings like this and hearing from you and iterating through a lot of our development to make sure that both the science is sound, we're marching in the right direction that way, but also that we're communicating and providing useful documents, useful aggregated statistics, and all that. So I'm going to close out my talk by kind of telling a little story about how I went through this process of kind of coming up with an analysis that I thought was clever, and then realized I had to try to make it useful too. So a lot of this work comes from an effort from last year. I was approached by Joe Fargione from the Nature Conservancy and Kevin, And there was a group of governors who were forming the U.S. Climate Alliance. They wanted to maintain goals of the Paris Climate Agreement. This map might be a little on the nose, red state, blue state. I assure you this is just pre-settings on the graphing software that I did not change. And if you don't believe me, you'll see I use these same colors later for different things. So one of the big goals was to take that NASA accounting that we'd done and some of the data synthesis we'd continue to do through the Coastal Carbon RCN, and to downscale it, essentially chop up those maps and make them available to the states. But it wasn't as easy as that, because we were really, in that NASA project, we were really considering kind of the total of the carbon cycle, and that's not super useful to a researcher on the ground who's like, okay, I want to dig a trench there and restore that wetland. I don't really care about like all the loss in Louisiana, as bad as that is. I just kind of want to know what I can affect with my management decisions. And so part of this project was coming up with a paradigm for sorting out the emissions and removals we had already been mapping to make metrics that were useful to landowners, or to stakeholders. So we decided to categorize things as manageable emissions and unmanageable emissions. So with manageable emissions, we decided that we would classify a certain fraction of methane emissions from impounded wetlands that we mapped as manageable. So that involved layering on an extra set of spatial data. We used the National Wetlands Inventory. There is a impounded map classification in there. And then we made some educated assumptions about how many of those impounded wetlands, what fraction of emissions were restorable from them. We also looked at the missed opportunity for carbon burial in drained wetlands. So we looked at both wetlands that National Wetlands Inventory said were drained, and also any agricultural, urban, or vegetated land that was below the high tide line, and assumed that's probably a drained wetland, and that's missing out on carbon burial. So we can say, hey, if you restart carbon burial there, you can probably, that's a net uptake. And then unmanageable emissions, any carbon burial or methane emissions from natural or undisturbed wetlands, we figure we'll just kind of leave those out of of this set of recommendations. And any catastrophic soil or biomass losses, even though they may have ultimate human causes, that they're not really attributable to a land manager, and not everyone has, at the scale that a lot of the decisions are being made, there's not a lot to do about those without more concerted top-down action. So this kind of just shows the how we parse those emissions. You have manageable emissions on this side, unmanageable on this side. This is for the entirety of the continental United States, and we're just going to play with the data a little bit. I'll show you a couple different versions of this. You see, like, oh yeah, the manageable emissions, it's a pretty small sliver of the overall emissions and removals for the whole U.S., but we know that Louisiana is a big deal, so take a look at this purple box. We'll see these soil loss events that really shrinks when you just leave Louisiana out of the thing. And if you just look at those climate alliance states, you can see that these manageable emissions is a pretty good chunk of what's going on out there in terms of the removals and burial. So this is a figure. See the blue and the red again? Presets in ggplot. So we made some kind of educational documents just summarizing this first cut for the Climate Alliance Learning Lab, which I think was in like September of last year, about this time last year. We found that missed carbon burial is by far the largest manageable emission. Kind of looking state to state, we found some interesting things. California has a really high proportion of this missed carbon burial opportunity because of the Sacramento Delta. Oregon actually has a really high proportion of tidally impounded wetlands. And so we thought this was a pretty clever analysis. We made these little one-sheets that we distributed to the state delegations who were kind of doing exercises, planning, and comparing multiple types of these natural climate solutions, and kind of creating theoretical portfolios of how they would accomplish certain goals. I attended this with Stephanie Simpson. We were the blue carbon roving experts, and I put that on my CV now. I rove, and I am an expert in something. It turns out that this was a good example of actually like listening to people and learning what they need. It turns out that this looked nice, but what they really needed was like baseline numbers of the areas of these different wetland types, soil stock estimates down to a meter for natural wetlands, so that they could go to their higher ups and say, hey, these are some like really baseline statistics for why this should be even on our radar. And so this is the kind of thing that being there at the Learning Lab, they can develop that on the fly and kind of be responsive to those to their needs. I am working with Kevin still, and a lot of this is still in preparation. We want to keep moving this forward. We have some issues, and I'll be transparent with those. First, this National Wetlands Inventory, these maps of impounded wetlands and drained wetlands, they're not consistent. This is not like this type of a product, or the National Wetlands Inventory. It's long story short, these features could potentially be overmapped or undermapped. We think that they're undermapped, but it's like it's one of these unknown unknowns. So even if National Wetlands Inventory isn't perfect, if we can get data on the accuracy of these classifications, we're in business. The Coastal Change Analysis Program itself, the underlying data set behind this, the salinity classifications in it don't really lend themselves to clean differentiation between high and low emitting wetlands. And so one of my big recommendations and hopes for the remote sensing community is that we get more methane relevant salinity classifications of our wetlands in our national scale mapping products. And then we could likely put some more work and better bounds on the potential for restoration to reduce methane emissions. And one of the big needs is to move a lot of these CO2 equivalent fluxes over to marginal abatement costs, which I need to understand better myself. So if you're going to ask me questions, not that. But to summarize my whole talk, I think that these last few years, we've made progress in top-down inventorying, relying on available maps and emissions factors. But this has also revealed the shape, scale, and sources of uncertainty. The Coastal Carbon Research Coordination Network is trying to move the science forward by fusing data and models, but we need support from partners and end users like you. We're kind of running on a PBS model right now. If you want us to keep moving and doing what we do, chip in a little bit of money, help us like strike up a collaboration. That's the kind of thing that we're interested in. And then finally, we really need key improvements to salinity maps and spatial and temporal data on impoundment, drainage, and restoration if we're going to scale up this manageable emissions paradigm and offer on-the-ground support. That's it. Thank you.